Okay, let's see.
People tell like when the position is like greater than a certain amount. That would be C. Or is it gonna be like closer to the stuff from 19 to 26? 4.
Oh, no, it's not going to be as complicated as that.
And we won't actually know how to use like the secant line, right?
No, but that shouldn't be too difficult, right? Because
Yeah.
you're always going to be provided two ordered pairs.
Okay.
And then you find the slope between those 2 points, that's your slope, and then pick either point slope.
Okay.
Probably not. Okay, yeah. Yeah, probably not. That was more from last quiz. All right, page 23. Start. Okay, function g has a derivative g prime, where g prime is decreasing and twice differentiable. Selected values of g prime are given in the table. It's given that g of 1 is equal to 2. What can conclude using mean value theorem in the interval from 1 to 10? Okay, well, mean value theorem allows us to gather information about the function below it. So, and gather information about g double prime using g prime. Right, so we know it's twice differentiable, so, and then they tell us the endpoints to use. So I'm going to use 1 and 10. So since we know we have g prime, so we can do the slope of g prime. Whatever we get from the slope of g prime, we know has to show up on the g double prime. So change in g prime over change in x. G prime of 10 is 0. G prime of 1 is 9. We know that there must be a value of G double prime equal to -1, even though we don't see it on this table, right? We know that IVT is not going to guarantee a G double prime of -1 because it doesn't have to dip all the way down to that value. But by looking at the slope of G prime, we know if these two endpoints is providing a slope of -1, there's no choice but for G double prime to actually hit that -1 somewhere between. Okay, left Riemann sum with 3 subintervals. Calculate, indicated in the table to approximate the integral from 1 to 10 of G prime of X. We want to find the area under the G prime graph. We can create our brackets here to indicate the width. And we're always subtracting the X values to get the width. 3 minus 1 is 2. 4 minus 3 is 1. 10 minus 4 is 6. It's a approximation, so we know it's squiggly line because we don't know it's not, we know it's not the exact area, just area of these rectangles. So we want a left Riemann sum. So the width here is 2, width here is 1, width here is 6, width times height, width times height, width times height. Now, it says, is this an over or under approximation of the actual value of the definite integral of G of 1 from 1 to 10 to G prime? Well, the hint here is that this G prime graph is always decreasing. So if my graph is always decreasing and I have a left Riemann sum, what do you guys think? So I'm attaching every left endpoint of every rectangle to the curve, and then I'm creating my rectangle over approximation. Okay, part C. Evaluate the definite integral from -1 to -3 of G double prime of 1 minus 3x. Show the work that leads to your answer. We know G double prime is going to rise to the G prime, but there's a little bit of messiness inside the parentheses. We got to go through use substitution so that we can keep track of all the pieces that's going to rise with it. some students have asked, can we do chain rules? So chain rules for derivatives, okay, use substitution is the integral version basically of chain rule, kind of putting things back together. Okay, so we let our u value be the parentheses, and we know we're replacing that dx. Okay, push that negative 1/3 out in front. So nice and clean, we can apply the antiderivative rule here. G double prime is going to rise up to G prime level. Negative 1/3 will come along with it. So we took care of our calculus here. G double prime to G prime. We can now worry about the bounds, but we don't want to work the bounds just yet. We don't want to do -1 and 3 with u because there's a mismatch. Either we push this through the relationship between u and x, and then use this, or what I think most students prefer, bring the original variable back, and then therefore we can use the original bounds. Okay, evaluate the balance between -1 and -3. Some students have asked, wait, these are out of order, so shouldn't we put them in order? I really don't care if the bounds are out of order if I'm just doing it, algebraically. But if I'm trying to read the graph, I'm trying to read the graph from left to right, then I would prefer the bounds being flipped. But if you want to flip the bounds, you're more than welcome to flip the bounds. You can flip the bounds and just make sure you change the sign in front. So our answer should still match. But usually I don't worry about the bounds if I'm using first theorem to just plug in. Okay, so 1 minus 3 times -3, that's 1 plus 3, which is 9. 1 plus 9 is 10. Minus, and then there's another negative that shows up. -1 in for x, 1 minus 3 times -1, that's 1 plus 3, which is 4. Okay, so now it's easy because we can just go to our go to our table and just pull the values, right? G prime of 10, 0, G prime of 4 is 5. Okay, page 24. There's probably not going to be a L'Hopital's rule on this quiz, but we understand the process, right? Just don't want to forget the process, right? You plug the expression in, just one in to see what you get. If you get a real number, then great, you stop. But if you get a 0/0, you keep going. And the way you keep going is you find the derivative of the top, and then separately you find the derivative of the bottom. And that creates a new version of the expression, and then you reevaluate, and that should get you down to a real number. Again, different from quotient rule. The whole purpose here is to find the limit of an expression that is not giving us something that we can provide as an answer. So it gives us a workaround with that 0/0. Okay, so let's go down to part E. Function is defined by w of x. Find w prime of 2. So we've seen this process before on the previous quiz. Which method is involved here if I want to find the derivative of this? Chain rule and product. Yeah, so product first because it affects a larger portion of the problem. But then, yes, there's going to be a little bit of a quotient rule with that g prime of 2x. F prime g plus f g prime. F prime 3x squared becomes 6x. Back to f. Okay, g prime, the derivative of g prime of 2x, outside derivative, g prime becomes g double prime of 2x, and then multiplied by the inside function's derivative. That's the hard part. The hard part is building the derivative. Now you just replace all the x's with 2, and then use the table g double prime and g prime and g double prime to pull those values down. Replace all the x's with 2's. 12 times g prime of 4 plus 12 times g double prime of 4 times 2. G prime of 4, pull from the table. G double prime of 4, pull from the table. And just add those values together. Okay, part F. Given the differential equation, y prime equals 1 minus 2y times g double prime of x, let y equals k of x be the particular solution for the initial condition k of 1 equals 0. Then use the expression to find k of 3. So we're going to solve the differential equation first. We're going to solve for y. We're going to solve for c. But then after everything is said and done, we're going to use the specific function to then find a specific value at a different point. Okay. Okay, so we're going to solve this differential equation. I like to represent y prime as dy dx, so I can just see all the pieces that are in play. I like to cross multiply just to get all the numerators showing and not have to look at denominators. So cross product. Okay, we do see one thing out of place. We want the y's on the left, x's on the right. So everything related with x's is on the right, except for this 1 minus 2y. So we have to move this 1 minus 2y over to the left side, divide it over. Right, full separation, y's on the left, x is on the right. We have to go through a little bit of what on the left side? Substitution. There's going to be a little bit left over because that 1 minus 2y, but it should end up being 1 over u du, which is natural log. Okay. And the right side, we're just going to go through first theorem, make g double prime rise up to g prime, and no need for u substitution because there's nothing inside that parentheses except an x. Okay, we know natural log takes care of the left side. Let's bring our u variable, our original variable, back into our problem. So at this stage, we're done with the calculus. We just have to figure out a way to algebraically get to our answer here. So at this stage, everyone may go down a different path, which is fine. And because we're going down different paths, you may be getting a different C value than me because you may be solving for C at a different point than me, which is perfectly fine as long as we end up in the same place. So we should still end up in the same place, but sometimes students say, well, my C value is different from yours. That's fine because for me, I'm just going to try to clean this up a little bit before I solve for C because I like to try to get that negative 1/2 kind of move to a better place. So multiply everything through by -2. It's a way of kind of tidying up that left side here. Now, if I distribute the -2 to the C, it's still going to be a plus C. So I'm just going to let that -2 kind of fall into that C. Okay, so I can either raise both sides with base E, or I can solve for C at this time. I think I may have solved for C on the key here earlier because I see that, oh, this is an easy order pair here. It's not going to be too complicated, even with that natural log in the way. So I went ahead and I just solved for C, but I could wait. I could solve for Y first and then solve for C, but that order pair just feels easy enough for me to just get that out of the way. Okay, so 1 in for X, 0 in for Y. If I plug 0 in for Y, I get 2 times 0, which is 0. Natural log of 1 is 0, so that's nice. That's nice and clean. Negative 2 g prime of 1 plus c. Right? We go to our table. G prime of 1 is 9. Negative 18 plus c. I add the 18 over to the other side, so 18 equals c. Once I have my c value, I want to insert it back to where I started making that substitution. So I want that 18 to be at this stage. Okay, not back here because I didn't insert it into this equation. I inserted it into this equation. All right, so here's my updated equation. Right, so now the only thing left to do, well, sorry, two more things. We got to solve for y first, but once we get to the equation, then we can worry about this last part, which is just plugging 3 and finding the value. But normally, with differential equations, we're just trying to solve for c and trying to solve for y, or trying to solve for c and trying to solve for the dependent variable. Okay, so I want to solve for y, but I want to get that expression out from under that natural log. So I'll raise both sides with e as the base. E and natural log are going to clean up nicely. I'm going to drop the absolute value. Oh, so what I did here was I realized that the problem was not asking for me to solve for y. It's just asking me to find k of 3. So rather than spending all this time trying to solve for y, I can just go ahead and plug in my ordered pair because I already have my equation that I need to work with. So I'm just going to jump towards finding my my value. So I want to find basically k of 3. Okay? And all that means is plug 3 in for x and see what y gives me. Okay? So I'm already kind of at an unsimplified version of my equation. And so I'm just going to stop because it's not asking me to solve for y. It's ultimately asking me to find the value at this point in time. So I'm just going to jump ahead and solve for a particular order pair at this point. Okay, so 3 goes in for x. So now I'm looking for a numeric value. I'm looking for a numeric value. I'm no longer worried about trying to get that y by itself. Okay, g prime of 3 is 7. Negative 2 times 7 is negative 14. Negative 14 plus 18 is 4. Okay, divide both sides by negative 2, which same thing as multiplying by negative 1/2. So this is that's my y value. It looks like a function, but it's just really just a number.
How did you turn all of like ln to the absolute value of 1 minus 2y to 0?
So what happened was I plugged in the order pair 1.
Yeah.
and I plugged in 1 in for y. Sorry, I plugged in 0 in for y. So that becomes 0. And then I get natural log of 1 minus 0. And then which is natural log of 1. And natural log of 1 is 0. So let's just clean that up. Okay, page 25. All right, solving more differential equations. Let y of t be the temperature in degrees Fahrenheit of a cup of tea at time t minutes. Room temperature is 70 degrees. Initial temperature is 180. The room temperature, don't have to worry about. It's kind of built into the equation here. T's temperature at time t is described by the differential equation with the initial condition y of 0 equals 180. Use separation of variables to find an expression for y of t. So more separation of variables here. Okay, so here we want t's on the right, y's on the left. Treat t like you would in x. Okay. And don't lose the parentheses. The parentheses is to kind of help you keep your variables separated. Cross multiply. Okay, divide the y minus 70. That's the only thing out of place. Right? The negative 0.1, that's a leftover. We want to just or coefficient. We want to keep as much away from the left side as possible, especially if we don't need it on the left side. So I separated things in a way where I feel like it's a little bit easier to read. I can understand this is my u substitution. It's going to end up being 1 over u. I pull that negative 0.1 out. I've purposely put a 1 here as a reminder. Okay, really, I'm just taking the antiderivative of 1 dt. And that negative 0.1 is just hanging out. A little bit of u substitution on the left, but we shouldn't be expecting a whole lot from the derivative. Okay, 1 over u becomes natural log absolute value of u. Let's bring the original variable back. All right, I'm gonna try to solve for y first, and then eventually I can solve for c because they give me an initial condition to work with. Okay, so I'll raise both sides with e as the base. E as natural log cancels out. I want to drop that c away from this expression, so that plus in the exponent is going to turn into a multiplication at the base side. Okay, e to the c is just one big constant. I can pull that constant out in front. Drop the absolute value. Solve for y. All right, so I'm ready to solve for c here. Zero in for t, 180 in for y. Just trying to solve for c here. 0 times anything is still 0. E to the 0 is 1. That's going to go away. So C is by itself there. Subtract 70 from both sides. C equals 180 minus 70, which is 110. All right, so now that I have my C value, I'm going to insert it back to where I started making that substitution, and that's going to be my final equation. So replace that 110 and for that C. I know you see C's all over the place, but you want to put it into the place where you started making that substitution, right? Not in, and not at other stages. Okay, so part B, how hot is the T after 10 minutes? Well, we have an equation that's going to tell us the temperature at any moment in time. We can plug in 10 in for T and solve for Y. So at 10 minutes, make the calculator do the work for me. That's going to come out to be around 110.467 degrees after 10 minutes. So parts B and C, we're not even doing any calculus. We're just taking the equation that we built from part A and then just reusing it. So part C says if the tea is safe to drink when the temperature is 120, at what time is the tea safe to drink? So here is the other direction, right? We're given the temperature and we just have to figure out the time that it reaches that temperature. So we can just plug in 120 in for Y and then just algebraically solve for, figure out a way to get that T. So no calculus here, we're just solving a variable in an equation. So replace Y with 120. And then how can I get that T by itself? I'm just going to slowly move things away from the right side. So I'll subtract 70 first. 120 minus 70 is 50. And then next thing on a move is move that 110. So divide both sides by 110. 50 divided by 110 is 0.4455. I want to solve for T, but T is stuck in the exponent. The way to bring the exponent down, if I can take the natural log of both sides, that will allow. Okay. I flipped it. I flipped it. So working with this left side makes it a little bit cleaner here. I took the natural log of both sides. And on natural log of E cleans up. I get negative 0.1 T equals natural log of 0.455. And now I'm solve for T, divide by negative 0.1. And then I know after 7.5 or 7.8 minutes, the temperature of the T is going to be 120 degrees. Okay, page 26. At closing time at a shopping mall, the mall does not magically empty. There are customers completing sales, employees who have to go through closing procedures in the table below. Equals 0 represents the announced closing time of the mall. Negative numbers represent the time in minutes before closing, and positive numbers represent the minutes after closing. The total number of people in the mall at time T is modeled by a strictly decreasing. So this number of people is always decreasing. Once someone leaves the mall, they're not coming back in, right? So it's strictly decreasing. Twice differentiable, it's a smooth curve. Values of P of T is as the times are given. So there's not a rate, it's just number of people. So that means 25 minutes before closing, there's 750 people in the building. 15 minutes before closing, 420. When they announce closing, there's still 175 people in the building, probably employees who have to finish up. 10 minutes after, there's still 90. Then 30 minutes after, only 25 people remain in the building. Okay, part A, use the data to estimate P prime of -5. We don't have P prime, but we can estimate P prime because we can just find the slope between 2 points. We'll pick the 2 points that are closest. So we'll do change in P over change in T over change in time, change in people over change in time, and that'll give us it's something that will be it's related to P prime of -5. But it's an estimation, so we do squiggly line. Okay, so change in Y over change in X. So I get a negative 16.33. So what's the unit of this value? People per minute. So we know that 5 minutes before closing, our estimation is that people are leaving the building at a rate of 16 people per minute. Or number of people in the mall decreasing at this rate. Part B, use data in the table to evaluate the definite integral from negative 25 to 30 of P prime. Okay, we don't have P prime, so we can't really do Riemann sums in the sense of, because this is not the P prime that we see in front of us. But we do have first theorem that we can evaluate, that we can use, right? What's P prime going to rise up to? What's the integral of P prime? Let's just not worry even about the balance here. If I just gave you the integral of P prime, what would you say that's going to turn into? What's this? Yeah, that's right. Just P of T. You take the antiderivative, and then once you're up at the P level, then you can plug in your upper and lower bound. So I get P of 30 minus P of negative 25. So P of 30, number of people left in the building. P of negative 25. So in the context of this problem, well, first off, what is the units going to be? All right, we're at the P of T level. So P of T level is people. So, but it's negative. So what does that mean? What does that? There's no such thing as negative people, right? So what does that mean for the context of this problem?
$725 people have less ball.
Yeah. So this is the change in the number of people between these two time periods, right? So we know that between 30 minutes and 25 minutes, or 30 minutes after closing and 25 minutes before closing, there's a change in 725 people, and that negative indicates that there's 725 people less in the building between these two time periods. But yeah, so we can also say 725 people have left the building in this time period, 25 minutes before closing and 30 minutes after closing. Okay, part C, approximate the average number of people in the mall by using a right Riemann sum with 4 subintervals. So average number, so we're thinking average value theorem. So let's write out average value theorem and for this particular problem. 1 over b minus a, integral from a to b of p of t dt. So we're going to accumulate all this huge number and divide it by the number divided by the time, and we can figure out the average number of people in the mall in this time period. Okay, our a and b values are negative 25 and 30. Okay, right Riemann sum. So each subinterval, subtract to get the width. Multiply by the right y value, so 10 times 420, 15 times 175, 10 times 90, 30 times 25. That's going to get you to be a really, really large number, but then we're going to divide by 55. And that's going to get us 149.545. So we know the average number of people in the building or in the mall throughout this whole time period is around 150. Underestimation, because it's a decreasing graph, but we're doing a right Riemann sum. So any rectangle where the right endpoint is touching the curve, it's always going to sit below the curve. Yeah.
What if you just say that because 149.54 is greater than 0? Just didn't talk about that, how it's like it's less than 0, it's an over approximation. It's one in-
Well, that's if we're if we have the concavity of the graph. Right. We don't have the information about the concavity because if we have concavity of the graph, then we know the graph is concave down. But this is not quite the same thing because the concave down, concave up is for linear approximation. This we can draw it out by looking at the curve and the way the rectangle is related to the curve. Okay, for part D, between in this period, 25 minutes before closing and 30 minutes after closing, function P models the number of people in the mall. It has the first derivative of P prime. Based on the model, how many people were in the mall 5 minutes before closing? So we're going to use the data to gain more accuracy in the sense that, if we know how many people are in the mall at 15 minutes before closing, that's going to be a way for us to gain more accuracy, right? Rather than choosing a time that's further away. So the closest to 5 minutes is before closing is 15 minutes before closing. And then we can figure out using the integral of P prime to figure out that the number of people who've left in that time period, and we can use that to subtract. So this formula shows up a lot. This final value equals initial plus displacements. So I'll choose the closest value to my goal. My closest value is 15 minutes before closing. I know that there's 420 people 15 minutes before closing, and I just have to figure out, what is the change in number of people in that 10 minutes from 15 to 5 minutes. And that will tell me. And if I can figure out how many people have left in that time period, and I add it to the people who've already who are still remaining in the building, we can figure out how many people are left 5 minutes before closing. Okay, so this is all calculator work. And this is our starting point. So we know there's 420 people to begin with. We know that in this 10-minute period, 191 people are going to leave. Yes. Because that's the closest to where I want to go, right? 15 minutes before closing, that's better than 25 minutes before closing. I'm sorry?
With 25 work as well.
It's not going to get as accurate of an answer. So you still get some credit, but the best accuracy is you want to use the closest to your target. Okay, I'll use the remaining time to just walk around, see if you guys have any questions.
Under conservation. We made it to that back, so we made this on. Goes with over potential, which is constantly negative, just can't be forgotten. But this one, it's also moving down. But how is this one?
Because this is a right Riemann sum. And this one is a left Riemann sum. So there's no need for you to memorize it, right? You just draw it out to feel convince yourself. If my graph is decreasing. And if I do a left Riemann sum, that means I'm attaching a left endpoint of every rectangle to the curve. I can see that the rectangles are clearly above the curve. It's over approximation. So never a need to memorize it. You should be able to just give yourself a moment to draw it out and convince yourself. Oh, I just plugged in the captain plugged in. Right, because P prime is this. So the depth integral of P prime is going to tell me the change in number of people in that 10-minute period. Which is negative. That one section. Oh, but like, that's for linear approximation, right? If I'm creating a tangent line and want to know what that tangent line is over approximation or under approximation, I think you're going to. It's the area under the curve over or under. I know we were saying word. And then so. It feels like you know it's very poor because if I know that there's opposite can be left. The P prime, I like to kind of.
No.
But I guess that could. Use that one. Zero. And did you ask? Zero. Did you ask? Did you ask? But it just feels right.
Yeah.
No. But you know, you do make it, you know, argument that that's that zero is closer, so I'll give you credit there as well. Good. Yeah.
Okay.
Because the original one actually had this as possible.
Oh, yeah.
No, but if you want, you do want to know how we can then. Yes. It says first. Actually, it's plus the X on it, give you one. See what you get. So you don't know, I'm saying, no, there's nothing in it. Zero. So we just do the first. But I think if you're really something, I'll be. Whenever the word is, there's not social, it's just small, but it's not a person, it's not a big one. Yeah, it's like usually-
What is
It's target, expression.
Yeah.
Don't get to give this.
It's no.
I think if you notice, 0/0, I can't either grade 5 or again.
Yeah, that's funny. I'm saying that the color of the.
Typically, problems like this, it's really, it's like, oh, there's 0/0. It's also. It's just going there with the stuff. I guess all my kids on this is so much. Should be in there. Yeah, some variation. Yeah,
Oh. I don't think that way. So, I don't know.
You don't have to.
That is the biggest issue.
Okay.
That's right, since she's so. Really sadly. If I feel so, that's something wrong for you, no, well, I don't, it's one for, I think.
You get negative one.
So I have a formula for P prime. So I just inserted P prime integral P. Makes it P. Equal to negative 5 of P prime. Right, we're not doing this by hand, we're just making that we're doing this.
I have no idea, I'm just like. The church made me. Yeah, I took my physics.